All right, hello guys, good morning. First time we've ever done this, so we're going to give it a shot. Hope it goes pretty well. So we're going to start off, you don't necessarily have to take notes here, we're just going to talk. So we've got a sphere. All right, let's say that this sphere starts shrinking, it starts getting smaller. I want you to think about for a second, what about this sphere is going to get smaller? Think of like the geometric terms you've learned, and what about this sphere do you think is going to shrink? Well, we know that the volume of the sphere is going to shrink. We know that the surface area of the sphere is probably going to shrink. We know that the diameter of the sphere is going to shrink, right? The distance from one side to the other. So, like, if I'm going to draw that right here real quick. Right, so if that's the diameter of this sphere, and the sphere starts getting smaller, then we know that that is going to shrink. We know that the radius is probably going to shrink then, if the diameter does too. And let's see what else. We know that the circumference is going to circumference. There we go. We know that that is going to shrink as well. So what we're going to learn today is one of my favorite topics in calculus, and I'm a little upset that I'm not going to be there today to talk about it. It's called related rates. And the idea is that when certain entities are changing, like in this case, when geometric figures are growing and shrinking, then all of the different components of those figures are also shrinking or growing, and they're doing so at different rates, and they're related to each other. And we're going to look at that today. So go ahead and pull out your guided notes. Let's take a look at this. A spherical snowball with an outer layer of ice melts so that the volume of the snowball decreases at a rate of 2 centimeters cubed per minute. All right, so basically you've got a snowball. Its volume is decreasing at a certain rate. And the question is, how fast is the radius changing when the diameter of the snowball is 10 centimeters? That's the question. So below that, in your guided notes, you see an acronym. You see DREDS. DREDS. Get used to that. You're going to see it a lot over the next week and a half, and probably aptly named because you will dread doing this. Okay, that's enough fun. So first, I'm going to take you through what each of these means, and then I'm going to walk you through this example. So the first part, and I want you to write this under the first D there, stands for diagram. All right, this is where we take the information that we were given in the problem and we draw a picture if it's necessary, and we write down all of the essential information. So we've got a sphere, right? So I'm going to go ahead and I'm going to draw a sphere. That's not awful. Okay, and that's my snowball. All right, let's see what else. It says the volume of the snowball decreases at a rate of 2 centimeters cubed per minute. How fast does the radius change when the diameter of the snowball is 10 centimeters? Okay, so I'm going to go ahead and draw a diameter here. And we know that's 10 centimeters. All right, cool. Now, other than drawing it, I'm going to write down the numbers that they've given me, and I'm going to say what they mean. So we know that the diameter is 10, so I'm going to write that here. And this should all go in that box next to that first D up there where it says diagram. So I know that the diameter is 10. And it says that the volume of the snowball decreases at a rate of 2 centimeters cubed per minute, right there, right? Now, it's not saying that the volume is 2 centimeters, right? This is very, very important. It's saying that the volume of the snowball decreases at a rate of 2 centimeters cubed per minute, all right? Now, every time in calculus we've talked about the rate at which something is changing. That means the derivative. So we are going to write down this information. We're not going to say that the volume equals 2. We're going to say that the rate at which the volume is changing, dV, equals negative 2. All right, it's negative because it is decreasing. So we have that the diameter is 10 centimeters and the volume is changing, represented by dV, equals negative 2 centimeters cubed per minute. All right, so that takes care of all of the information that we know. That takes care of all of the prerequisite work we have to do. Get this down, pause it if necessary, because I'm about to delete all of that stuff. And there it goes. All right, so next, R stands for rate. And that means what we are looking for. All right, it's what the question is asking for. So looking here, it says how fast is the radius changing when the diameter is a certain length, in this case 10 centimeters. So it's not asking for the radius itself. All right, that's important. Oh, I don't want to do that. I want to draw. Okay, there we go. It says how fast is the radius changing. So it doesn't want us to give it. It doesn't want the radius. It wants the rate at which the radius changes. So next to the r there in that box, write dr. All right, that's what we're going to be looking for. That's the end goal here. Is the rate at which the radius is changing. Dr. Easy. Get rid of that. Okay, next. E stands for equation. We need, oh, it's green, whatever. We need to create an equation that is going to use all of the information we have. Now, if you think about a sphere, if you think about a circle, there's a ton of equations we could use. We could use the area of a circle as pi r squared. We could use circumference as 2 pi r. We could use surface area, and I'm embarrassed to say I don't know what that is off the top of my head. Or we could use volume, which is 4/3 pi r cubed. And we are going to, in this example, use volume, and I'll tell you why here in a little bit. But for right now, in the equation box, go ahead and write V equals 4/3 pi r cubed. All right. So that's done. I'm going to leave that up there because the next step, the second D, stands for the derivative. We are going to take the derivative of that function. All right, now, related rates are kind of like implicit differentiation in that we've got two variables here. Right? We have volume. Oh, gosh dang it. There we go. We have volume and we have radius. All right. So when we take the derivative of this, we have to include the rate at which those things are changing. If the function is volume, then the derivative is the rate at which the volume is changing. So the derivative of v in this case is going to be dv equals, so we're going to do the power rule here. So we're going to bring this 4 pi is technically a coefficient for r cubed. So we're going to bring the 3 and multiply it. I'm not sure why this is messing up so bad all of a sudden. 4/3 times 3 is going to be 12 over 3, which is 4 pi r, and then 3 minus 1 is squared. So again, just regular power rule there. And we took the derivative of r, so we have to add dr, the rate at which the radius is changing. All right, so again, reiterating, derivative of volume is dv. Power rule to get 4 pi r squared, and then we have to include the rate at which the radius is changing. So that's going to be our derivative right there. Make sure you get that down because I'm going to have to erase all of this. Now, you might think that that was kind of redundant because we now have 3 variables where before we had 2. We've got dv, we've got r, and we've got dr. But if you look at the information that we are given, you'll notice that we already have a lot of this information where we didn't have it before. All right, so for example, dv. Well, if you look at your diagram in the first step, we know that dv is -2. I'll do this in a different color. We'll do this in blue. We know that dv is -2. That's done. All right, 4 pi. Now I've got r squared and I've got dr. And according to the second step where we named the rate, I know I'm looking for dr, so I'm not going to be able to substitute for that. So I somehow have to substitute in for this r here. And it never explicitly told me what the radius was, but it did say that the diameter of the snowball is 10 centimeters. And that means that the radius is 5. 5 squared dr. And then once we've substituted, we can solve. 5 squared is going to be 25. 20 times 5 times 4 is 100. So negative 2 equals 100. And this is still in that last step, and I didn't actually write what that stood for, so give me a second, I'll do that. 100 pi times dr. To get dr by itself, we're going to do negative 2 over 100 pi equals dr. So our answer is going to be negative 1 over 50 pi equals dr. Now, this represents the rate at which the radius is changing, and the radius is changing at a rate, it's not just a number, we have to add a unit. So if the volume is decreasing at a rate of 2 centimeters cubed per minute, then the radius is going to shrink at the same, within the same units in the same amount of time. So it's going to be negative 1 over 50 pi centimeters per minute. All right, it's just centimeters. It's not squared because we're not dealing with area, and it's not cubed because we're not dealing with volume. So that's going to be our final answer there. All right. And so what that means is that when the diameter of the snowball is 10 centimeters long, the radius is changing at a rate of negative 1 over 50 pi. So going back real quick, that last step, what did we do? We substituted. You could also say solved, I suppose, if you wanted to, because we solve it as well. But I like to say substitution because we put those values in. All right. Couple of loose ends I want to tie up, or questions you might have. First, go back to the equation. Why did we pick v equals 4/3 pi r cubed? Well, let's pick a different example, and I'll show you why. So let's say that, you know, I'm thinking of a equation that has to do with circles. Let's use, I don't know, let's use area. Let's say area equals pi r squared. All right, because you know it's got an r. We talked about r earlier, right? Cool. Okay. So next step, right? We're going to take the derivative. So you get dA, the derivative, the rate at which the area is changing, equals, bring that 2 down, 2 pi r, 2 minus 1, that's just going to be 1 next to that r, and then the rate at which the radius is changing. Well, I know that r is 5, but I don't know dr, right? Because I'm looking for that. And this the rate at which the area is changing, dA, I have no information in the original problem that's going to give me that answer. All right, I cannot find dA here, so that's not going to work. They gave us the rate at which the volume is changing, so we have to use an equation that involves volume. You know, try another one. Let's use circumference, right? So circumference of a circle is 2 pi r. So if we take the derivative of that, you get the rate at which the circumference is changing, dc, equals, let's see, that's 2 pi r, so that's just a coefficient, so it would be 2 pi times dr. We don't have dr, we're looking for that. We don't have dc, that's not going to work. So you see why we use the volume formula. And when you're working on these problems in class today, I mean, you might have to try a few equations before you find the right one, all right? Because you have to use the information given in the problem to figure it out. All right, next, going back to the equation, volume equals 4/3 pi r cubed. Notice we took the derivative and then we substituted. So you may be wondering, why couldn't we just plug the r in? If the radius is 5, why can't we just plug it in here instead of instead of after we take the derivative? We're going to get more into this a little bit later, and we'll certainly have plenty of practice. But basically, this represents, right, this function right here represents the volume, like it's just a general volume equation. All right, the radius of this snowball is always changing. If the snowball is melting, if the snowball is shrinking, then the radius is always changing. Okay, so we can't put it into the to the formula yet. However, when you take the derivative, dv equals 4 pi r squared dr. Now we have the rate at which the volume is changing, the rate at which the radius is changing, and now we can plug it in here because it's the radius at the specific instant that the diameter is 10 centimeters. The diameter is not always going to be 10 centimeters, which is why we can't plug it in up here. But down here, now that we have these units, the rate at which things are changing, I can go ahead and plug it in. So basically, long story short, if that confused you, Don't plug anything in until after you've taken the derivative. All right, that's all I've got. You guys have homework sheets to work on now. If you have any questions, you're welcome to shoot them to me over Twitter. And I'm looking forward to getting back and practicing with you more a little bit tomorrow.